大家好，我很高兴回北京。Don't worry, I'm not going to be doing the rest of my presentation in Chinese. I'm Amanieu. I actually grew up in Beijing in China as a child. I lived there for 13 years. Today, I work as part of the Rust project. I'm leader of the library team, and I also work on various parts of the compiler and the ecosystem. I'm a consultant for Huawei's trusted programming language lab in Ireland, and I also founded a startup working on dynamic translation, binary translation software, which if you have bought a phone recently in the past year, it may actually contain our software to support running 32-bit applications on Android on newer phones. But the main topic of this talk is the register allocator in Cranelift. So let's start by looking at Cranelift itself. Cranelift is an open source optimizing compiler backend written in Rust. So you can think of it as something similar to LLVM, but it has more focus on fast compilation time. It supports 4 different architectures, and it was created back in 2016 and is now maintained by the Bytecode Alliance. There are 2 main users of Cranelift, and these are GOSIM, a WebAssembly runtime that's written in Rust, and Rust C code in Cranelift, which is an alternative compiler backend for the Rust compiler, since the Rust compiler normally uses LLVM. And because of its fast compilation speed, Cranelift is also used as a JIT compiler in several other projects. So what is an optimizing compiler backend? Well, let's have a look at the compilation process. A compiler is a tool that takes some input and transforms it into executable code, executable machine code. And this input can be anything. It can be WebAssembly bytecode, it can be Rust code, it can be JavaScript, it can be even more exotic things. For example, in a binary translator, it can be machine code for a different architecture that you're translating to the host architecture. You can have a compiler that directly translates the input, whatever it is, into machine code. But if you're writing an optimizing compiler where you want to improve the code in various ways, then what you will generally want to do is translate this input into an intermediate representation on which you can perform optimization passes. That is what happens here in the middle end. And after you've done all your optimization passes, you then have the backend that converts this intermediate representation to assembly code. So Cranelift is a combination of the middle end and the back end of a compiler, just like LLVM. So let's have a look at the intermediate representation used in Cranelift. Here on the left, you can see a Fibonacci function, returns the nth Fibonacci number. Fairly straightforward. And on the right side, you can see the Cranelift intermediate representation that is generated by the front end for this function. Some things that immediately come out is that you'll notice that each value defined as v0, v1, etc. is only defined once in the intermediate representation. This is called static single assignment form. And the way this works is that if you ever have control flow joins, so where control flow needs to needs to jump to a single block from multiple predecessor blocks, you'll generally, as you can see in block 1 here, which is the loop header, which can be reached either from the entry block, block 0, or from the loop block in block 2. That block will have arguments which represent essentially incoming values that come from different blocks. The fact that each value is only defined once is a very useful property for various optimizations, and we actually take advantage of this in the register allocator to simplify some of the analysis, as you'll see later. So let's take a deeper look at just the backend part of the compiler. The middle end will essentially do a lot of optimizations, but in the end, all it does is take an existing intermediate representation of a program and transforms it into a different intermediate representation. The backend is a bit more complex because it takes the intermediate representation as input and then processes it through several stages to generate assembly code. The first stage is instruction selection. So on the top left, you'll have just intermediate representation that performs an addition and a subtraction. And in the intermediate representation, constants are represented as a separate instruction. However, if we lower this to x86 instructions, we realize, well, we can actually just put the constants directly in the instruction. So instruction selection produces instruction templates which describe what values each of these instructions takes as inputs and outputs. So for example, here you can see that the add instruction takes v0 as an input and produces v11 as an output, with a constraint that the output register for v11 must be the same as the register selected for v0. This is due to the x86 instruction only having a single operand to specify the first input and the destination. The goal of register allocator is to select physical registers for each of these operands according to the constraints that are given, and if necessary, insert move instructions to move values between registers and also between registers in the stack. Finally, code generation will take the output of register allocation and actually generate the instruction encodings for the instructions that were selected and the registers that were selected. So let's take a deeper look at the register allocation problem. Most instructions can only operate on registers. They can't access memories. Generally, only load and store instructions are able to access memory. And CPUs have a limited number of registers. This will vary between 8 and 32 depending on the architecture. However, the intermediate representation can have an arbitrary number of values. It's not uncommon to have thousands, tens of thousands, hundreds of thousands of values in the intermediate representation. So how do we map a potentially unbounded number of values to a small set of registers? This is actually a very easy problem. Just assign each value a location on the stack, of which we can also allocate an arbitrary amount. And then before every instruction, load values into registers. And once the instruction is done, write the result back to the stack slot for the value. Done. We have solved register allocation. The efficient register allocation problem is when you realize that actually moving values between registers and memory is expensive and actually has a cost. Moving values between registers is also, it's less expensive, but it's still a cost. And we want to try to avoid it as much as possible, but especially we want to try and avoid doing these things in the middle of our hot loops. This is actually a hard problem, and it's NP hard, which means there's no efficient solution that there's no way to compute an optimal solution in a reasonable amount of time. So compilers have to use heuristics, but even using heuristics, in Cranelift, for example, register allocation is half of the total compilation time. So let's look at the different register allocators that Cranelift has gone through. There's been quite a few rewrites. The original Cranelift register allocator was written in 2017, along with the initial implementation of Cranelift. This is actually by the same author as the LLVM greedy register allocator, which is still in use today. In 2020, there was a complete rewrite of the Cranelift backend, and this rewrite used a new register allocator called regalloc.rs, which was developed as a separate crate. That crate actually included two different register allocator implementations: a linear scan fast allocator and a backtracking slower allocator. In 2021, there was another rewrite of regalloc.rs called regalloc2, which was based on the design of the register allocator used by the JavaScript compiler in Firefox. And recently this year, a fast backend was added to regalloc2, which runs about 6 times faster, but generates worse code. Finally this year, I've been working for the past 9 months on a new register allocator called regalloc3, which is heavily inspired by regalloc2, but also by the latest developments in the LLVM allocator. One thing to note about all these allocators is that at every transition between two allocators, Cranelift has supported both the old and new allocator. In the case of the backend rewrite, this was done by just supporting two completely separate backends. But for the different regallocator crates, we did this in a bit of an interesting way, in that regalloc.rs got added an option to use regalloc2 as a backend, and similarly, regalloc2 has an optional backend that you can select using a configuration option to use regalloc3. So this makes the transition very easy, and also makes it easy to compare the performance of the different allocators. So why did we decide to make an independent register allocator? Well, traditionally, the register allocator is deeply tied into the compiler backend. It will use all sorts of internal data structures of a compiler. If anyone has tried to look at the GCC or LLVM register allocator, it's a pain to extract into a separate module. For Cranelift, apart from the original register allocator implementation, we decided to make this a separate crate, and has several benefits. One benefit is that this gives the register allocator a clean interface, which means it's very easy to test it in isolation. The other benefit is that it allows collaboration, since the register allocator can now be used by other compiler projects. Now you may ask, why don't these projects just use Cranelift? Well, Cranelift is a general compiler backend. It may not be suitable for all cases. For example, things like if you're building code with a specific ABI, or if you're doing something exotic like a GPU compiler, which needs special register allocation rules. So let's have a deeper look at the input for the register allocator. This is the API, well, a part of the API for regalloc3. It doesn't include everything. Refer to the source code for the full definition. I'll provide a link at the end of this talk. The input essentially consists of two parts. First, a reginfo. Well, you need to provide a type that implements the reginfo trait, which will describe what is the register structure of the machine you're trying to compile for. How many register banks do you have? How many register classes? How many registers? For each class, what registers it contain, etc. you're essentially describing all of the constraints that may be used in a function. The other half is the function trait, which describes the function you're trying to run register allocator on. So this will include information like what are the number of basic blocks, what are the number of instructions, what are the instructions in each block, what are the operands in each instruction. And the operands essentially consist of two kinds. They are either define value or use an existing value. And along with each operand kind, there's also the constraint, which can be a class, meaning this operand can be any register in this class. It could be a fixed register. This operand must be allocated to this fixed register, or it could be a reuse constraint, which means that an output operand must use the same register as an input operand. You'll notice that in here, everything, so instructions, blocks, values, registers, these are all new type wrappers around integers. This is really a query-based API where we just ask the register allocator client any information that we need to run register allocation. The output of the crate is essentially two things: the stack layout, about which value, how much stack space you need to allocate, and the output instructions, which is an iterator that produces this enum on the left. Either it tells you whether for each block to generate an instruction and the allocations for each operand of that instruction, allocation being either a stack slot or a physical register. It could be to rematerialize a value, so for example, a constant, to just regenerate this constant into the given allocation, or it could be to move the contents of one allocation to another allocation. So let's look in detail. How do we get from the input to the output? The basic algorithm has 6 steps, and I'm going to go through each of them in detail. The first step is computing value live ranges. On the left, you can see a simple program defines a few values, branches to either block 1 or block 2, and then these two blocks join up at block 3. For each of the 3 values defined in this small function, we first need to calculate for each value what parts of the function it is live in. And this is done at a higher granularity than just the instruction boundaries. We actually have 3 different points within an instruction where a live range can start or end. There's B, which is the instruction boundary, early def, which we're not going to talk much about in this talk, but the other one is the normal use in def, which basically means that the use of value ends at this point and the definition of a value starts at this point. So the live ranges are essentially as listed here. For example, value 0 is used from instruction 0 all the way to where it's defined, all the way to instruction 4 where it's last used. But it's also used in block 2, which means there's a separate section of the live range which starts at the start of block 2 and ends on the first instruction of block 2. Similarly, we have use lists for each value where we keep track of where the value is used. The second step is value coalescing, where we have values that are used across multiple blocks, that are used in particular in basic block arguments, for example, instruction 5 and 7. Normally, if the value 1 and 3 are allocated to different registers, then at the point of the jump, we need to insert a move. We want to try and avoid this, so we try to merge live ranges together. We can only do this if the live ranges don't overlap. So for example, we can merge 1 and 3 into a single live range, but once we've done that, we can't merge 2 because 2 overlaps with 1. So we can either merge 1 and 3 or 2 and 3, but not both. And this ensures that these two values are allocated to the same register, and it avoids a move instruction. The next step is building virtual registers from the coalesce values. In this example, it's very straightforward. For each of the coalesce live ranges, we build one virtual register. We also, for each virtual register, track two things. The class the register class, which is the constraint that it needs to satisfy. In this case, this is the union of all the constraints on the different uses and definitions. And the spill weight, which represents approximately the density of how often this value is used. And this is calculated as the number of uses or definitions divided by the length of the live range in instructions. So what we're going to be doing now is the main allocation loop. We're going to, for each virtual register, try to assign it to a physical register. To make things more interesting, we're going to do this on a machine that only has 2 physical registers. So we're going to start off by trying to allocate V0. It's easy. Try to allocate it to R0. It works. It doesn't conflict with anything that's there. Similarly, we're going to try and allocate V1. We can't allocate V1 to V0 because V1 conflicts with what's already in R0. So we're going to put it in R1 instead. Now we come to V2, which is a problem because it conflicts with what's already in R0 and what's already in R1. So we can't actually allocate it anywhere. We also can't evict something that's already in R0 or R1 because V2 has a lower spill weight, so it's less important. The only thing we can do is to split V2 into 2 separate virtual registers. So here we've split it at the boundary 3b, which is just after the definition of the value. And we've created a virtual register V3 that's only 1 instruction wide and therefore has an infinite weight. We cannot split it further. We must allocate it. The other one, V4, actually has a spill weight of 0 because it doesn't actually contain any uses or definitions. And you'll notice it's assigned to register class 0, which means any register or a stack slot. So we're going to try and allocate V3. It has an infinite spill weight, so we will evict the existing value in R1, which has a lower weight. So now V1 has been evicted, and we've assigned V3 to R1. Now, we still need to allocate V1, and we don't have anywhere we can allocate it, so we're going to split it like we did last time. Split it into 3 pieces. The 2 pieces with the definition of the use have an infinite spill weight, and the piece in the middle has a spill weight of 0. We're going to assign the 2 pieces with infinite spill weight into R1 because it now fits. And then we are left with just the last 2 pieces with spill weight 0, which are the parts between any uses and definitions. We can't actually fit them anywhere, but because they have register class 0, they're allowed to be on the stack. We can just assign them to a stack slot. So now we're on to the spill slot allocation, where we basically do a similar algorithm where we try to allocate each spilled value to a stack slot, but instead of trying to evict or split the value, if we encounter any conflict, we just allocate a new stack slot. We have effectively infinite stack space. Now, at this point, we have assigned a location for each value, for each piece of the live range of value. We now need to connect all of these pieces with move instructions to ensure that values are actually kept somewhere at all times. So move generation works using a mechanism called half moves that I'll go into in a sec. First of all, what we need to do is, for each use and definition, record in the allocation list for every instruction what every operand of that instruction has been, what location has been assigned to each operand of that instruction. This is done because the use list keeps track of the index within each instruction where the operand happens. Now, for the actual moves, what we're going to do is we're going to go through every live range and gather a set of source half moves and destination half moves. The way this works is that, for example, here, we notice that this live range crosses a block boundary at, if I remember correctly, 4B, which means that there is a move from the block boundary at this block to any successor blocks. And we'll note these down as source half moves. Similarly, there are these live ranges intersect a block boundary for an incoming branch, so we'll generate a destination half move for these. We will also generate half moves for any values that were split into multiple pieces. So these highlighted in yellow are the split products from splitting V1 and V2. So we'll want to make sure we generate a move instruction to join them. And finally, we also want to generate move instructions for any basic block parameters. And for each of these moves, we know the allocation that one half of the move has been assigned. So what we will then do is we end up with a set of half moves that are keyed by the instruction at which the move happens and the value that's being moved. We're going to sort these and generate a set of edits, which are the final moves that are going to be inserted in our program. You'll notice we've eliminated some no-op moves from stack 0 to stack 0 and from R0 to R0. These don't do anything, so we've eliminated them. And then we're done. The allocation list and the edits list are basically the output of the register allocator. The output iterator will basically walk through the edits list along with the original instruction list and produce either this output iterator enum, which is either an original instruction or a move operation. There's a lot that I'm not actually covering in this talk due to time constraints. For example, parallel move resolution. When we're resolving the moves, we need to make sure that we properly handle things like swapping the values of two registers, because that actually requires a cycle in a temporary register. Similarly, we need to deal with we need to use scratch registers for things like stack-to-stack moves. Move optimization, this is a post-processing optimization pass which eliminates redundant moves. For example, if a value is spilled to a stack slot multiple times, we want to eliminate any subsequent spills. This is due to a limitation of the allocator that, for simplicity, we only track one location for each value at any time, though in reality the value can be located in multiple registers. There's also support for compound or overlapping registers for that are used on certain architectures, register groups, which are used for allocating sequences of consecutive registers. Also, other things like fixed register constraints, reuse register constraints that I haven't been able to cover. There is also support for rematerialization, which allows things like constants to be rematerialized out of thin air instead of forcing you to spill them to a stack slot and then reload them later. There's also a lot of thought that went into the various heuristics that were used for the allocation loop, for the splitting, etc. If you're interested in learning more, please come and see me after the talk. I'd be happy to chat with you. So obviously this register allocator algorithm generates good code and is pretty fast. How did we achieve a good level of performance? Well, one thing to notice is that by the time we get to register allocation, we're not going to be modifying the instructions anymore. The Cranelift IR is designed to be editable, which means that the various optimization passes that run in the middle end will want to insert instructions, remove instructions, make all sorts of changes to the IR. This is not necessary anymore when we get to register allocation, and in fact, it allows us to use a simpler representation. An editable IR essentially works in Cranelift works by treating the instructions in the block as a linked list. For register allocation, we prefer just having a flat vector of instructions that we can index directly. And it's worth spending some computation time to get the input IR into an efficient format. It makes sense if you think about it. You're going to have to do a lowering pass to turn the intermediate representation into a target-specific form as part of instruction selection. You might as well take the advantage of this to make sure all of the basic blocks are in a reasonable order. So, for example, ensuring that the definition of a value always appears before use in the linear order basically allows all of the register allocator algorithms to do a single linear pass over the IR. Similarly, on the output side, we never actually have to generate the modified IR with the move instructions inserted into it and all of the registers filled in. The output iterator from the register allocator just feeds directly into code generation. So another aspect is cache efficiency. We use a bunch of indices in the register allocator to indicate things like the index of a value, the index of a register, the index of an instruction, etc. And for those, we use a U32 instead of a usize. That's an instant 2x memory saving. We instantly have two times more CPU cache use. This is huge. These indices are used a lot in the allocator. Another thing is keeping track of small sets of values. For example, the use lists. Rather than using something like a small vec, which you might normally use for such small lists of values, instead we can just use a single vector for the entire function and then allocate subslices of that vector for the different for each value. So that way the use list of a value only takes up 8 bytes. It's 2 U32s. The downside of not using small vec is that you need to call the memory allocator more, and we can avoid that by actually reusing all of our allocations across multiple functions. So the register allocator is a struct that contains a bunch of vecs that are used by all of the intermediary passes within the register allocator. The idea is that you will run the register allocator on one function and then keep the register allocator struct around, which contains all of these temporary memory allocations. You will just clear all the vectors and then run the register allocator again on a new function, preserving all the allocations. And this basically eliminates the memory allocator from the profile when we're measuring performance. Another good thing is bit packing values into an integer. This saves a lot of memory and also makes searching and brain search faster. So if you remember, for live ranges, we actually have several points within an instruction. Realistically, we don't need all 32 bits to represent an instruction index. It's sufficient to just use 28 bits, and this saves us 4 bits to indicate a spot within the instruction. The fact that this combined value is itself just a U32 means it just works instantly with things like sorting and for hash tables. It's just much faster to hash a single U32 or sort a single U32. Similarly, being able to sort values and then just do a single scan over them is a huge win for cache efficiency. You saw this when we computed the final edits for the instructions. We sorted the edit list and then just went through it went through both the source and destination half moves in a single pass to combine them and generate the final edits. The final lesson is in testing in development, and register allocation is it's a very complex algorithm, and we need to be absolutely sure that we generate correct results. So testing is absolutely essential. So it was very important to create the right tools to enable us to test the register allocator. In particular, we have a text representation of the reg info and function traits, which we can dump which can be dumped and which can be parsed. This is great for small test cases. We have a validator that checks that the inputs to the register allocator is correct. If the inputs are correct, we guarantee that the register allocator won't panic or go into an infinite loop or anything. The fact that we have these validators means we actually don't need to bother with a lot of the checks within the register allocator. We just assume that the input is correct. Note that this is still all safe code, but that still means that if the input is correct, we guarantee no panics, no infinite loops, and that we generate a correct result. We have a generator that creates randomized reg info and function traits, and we use this as an input to a fuzzer. And we have a checker that checks the output of register allocation for a given function and runs it through some form of symbolic execution to check that the output of the register allocator, so it runs through all the moves, all the instruction uses, checks that all of the selected allocations match the constraints. And this has been huge for development because it gives you a reassurance that you haven't made any mistakes, and Rust is already great at this with the strong type system, but being able to have this extra layer just makes development much faster and much safer. So that's all I have to say. Thank you very much.